Legend foretells of a kingdom long forgotten, a utopia lost to the waves of history, ruled by the wealthiest man in the world, King Hamlet Burgess. It is said that there is a secret to his wealth, the 4 treasures that, when used together, would make anyone the wealthiest person alive. The 3 surrounding kingdoms, vying for such riches, released many monsters upon the king and his kingdom. With little time and no hope of escape, the king sent his most trusted knight to hide the treasures, leaving hints for his future heirs to reclaim them. Sadly, his heirs would never claim their birthright, as the kingdom was utterly destroyed. The king had left one clue for his children to help them find the treasure: a range of coordinates 00 to 88.
Let's break down the problem together. The problem is that while there are only 4 treasures, one for each king's children, the land is filled with 1,000 traps that look identical to the real treasure. With archaeologists' lives at stake and limited tools and resources, they must find a smarter way to search, using the king's clue to their advantage. Let's break down the problem. The clue tells us that the treasure lies within the range of 00 and 88, so we need a graph-like structure to represent the entire area. The grid we'll use is in 64 by 64 blocks, meaning that there are 4,096 individual dig locations. According to the inscription, every block that doesn't contain a treasure is either rigged with explosives or completely empty, so accuracy is critical. The specified range, 00 to 88, implies that we're working with a coordinate plane. Ultimately, we need to locate the treasure with the least amount of digging and least amount of splitting possible.
The archaeologists found an unconventional but effective method of locating the treasure. Introducing the BinTree, a spatial data structure that divides space by repeatedly splitting the map, first vertically, then horizontally. The BinTree helps us zoom in fast, skipping entire trap-filled regions and unlocking onto our treasure zone. Let's see how we're able to use it to find the treasures. We begin by slicing the grid vertically to center at x is equals to 32. Our target region lies entirely in the left half, so we discard the right. That's half of the map, eliminated by just 1 division. We're now down to a 32 by 64 grid, which has 2,048 blocks. Now, we slice horizontally at y is equals to 32. Again, our region is in the bottom left, so we eliminate the top half. Now it's a 32 by 32 grid, which has 1,024 blocks. We repeat the pattern and split vertically at x is equals to 16. Our target region lies on the left, so we keep only that quadrant. Now it's a 16 by 32 grid, which has 512 blocks. Next, we split horizontally at y is equals to 16. Now we're down to a 16 by 16 grid, which has 256 blocks. One more vertical split, this time at x is equals to 8. The treasure lies on the left again, and half the grid is gone. Now it's a 8 by 16 grid, which has 128 blocks. We do one more final division and the final split at y is equals to 8. We isolate the exact 0 to 0 and 8 to 8 target region. It gives us an 8 by 8 grid, which has 64 blocks, a tiny fraction of the original 4,096 blocks that we started with.
At each split, we eliminated half of the remaining search space, exactly what makes this a logarithmic process, making it O of log n. In just 6 steps, we narrowed from searching 4,096 blocks that included traps to just 64 blocks that are trap-free. Now that we understand how BinTrees work and why they're appropriate for this situation, what makes other techniques such as linear searches, PR quad trees, and KD trees less useful? A linear scan approach would be inappropriate for this situation, as searching through every zone would mean a lot of digging, as well as putting the team in danger of traps, as there's a 99.91% chance of hitting a trap or an empty block. So what about PR quad trees or KD trees? While PR quad trees are also O of log n time complexity due to their splitting nature that's similar to BinTrees, they also use a significant amount of resources. Creating 4 subsections with every split uses a large number of the team's resources and creates a lot of overhead when considering space complexity. BinTrees would be preferred over this method. KD trees would not be applicable, as we're looking for a range and KD trees split on a point. Specific points are required to use KD trees.
Found it. Let's see what's inside. Is that Why is he... Can't hear. That's it. I quit. I don't get paid enough for this, man. See ya.